So, hi everyone, welcome to the YouTube channel of ChemLover. From today onwards, I am going to start organometallic compound series. So, in this lecture, first lecture, we'll discuss metal carbonyl chemistry. Basically, there will be 4 or 5 lectures based on metal carbonyl chemistry, where we'll learn about how to determine metal-metal bonds in low nuclearity metal carbonyls and high nuclearity metal carbonyls. We will know about Wade's rule. We'll know about Wade's-Mingo rule, how to determine skeletal electron pairs, and then we'll know about carbonyl stretching frequencies in different metal carbonyls. So now let us start the topic. This lecture is very important for Csir Net, GATE and SET aspirants. So now let us start the topic, that is metal carbonyls. So now what are metal carbonyls? If we talk about metal carbonyls. Now, what are metal carbonyls? Metal carbonyls are basically the cluster compounds which contain metal-metal bonds. These are the cluster compounds or metal clusters. These are metal clusters which contain metal-metal bond. Metal clusters which contain metal-metal bond. Basically, we have two types of these metal clusters. There are two types of these metal clusters. One is known as low nuclearity. Low nuclearity metal carbonyls or metal clusters, low nuclearity metal clusters. So these will be simply represented by LNMC or LNCC, carbonyl clusters. Now let me write LNCC. These will be simply represented by LNCC, low nuclearity metal clusters or carbonyl clusters. Isn't it? And the second one is high nuclearity clusters or metal clusters, and these are represented by HNCC. So this is simply representation LNCC and HNCC. Now what are low nuclear metal clusters? Nuclear metal clusters are those in which the number of metal-metal bonds is less than 4. Number of metal-metal bonds is less than 4. So when the number of metal-metal bonds is less than 4, the clusters are called low nuclearity carbonyl clusters, isn't it? And when the number of metal-metal bonds is more than that of 4, then they are called high nuclearity carbonyl clusters. Now first we will study these low nuclearity metal carbonyl clusters. So our first discussion will be on LNCC, low nuclearity carbonyl clusters. So basically what we know about these carbonyl clusters, in this case there will be metal-metal bonds, but the number will be less than 4. There will be less than 4 number of metal-metal bonds. So first we should know how to determine this type, how to determine these metal-metal bonds. If we know how to, if we will come to know how to determine metal-metal bonds, then further we can determine the structure. So how to determine metal-metal bonds? Metal-metal bond determination. So there are few steps you need to follow for determination of metal-metal bonds, isn't it? Our first step is you have to determine total valence electron count of a cluster. Total valence electron count. So this thing is represented by TVE. First you have to determine TVE, that is total valence electron count. And then in the second step, you have to subtract this TVE from 18 into N minus TVE, means you have to subtract this TVE from 18 into N divided by 2. This will give you metal-metal bonds present in a compound, present in a carbonyl cluster. Isn't it? Now what is this 18? Basically this 18 comes from the 18 electron rule, and N represents the number of metal atoms present in a cluster. So now let us apply this rule and determine we'll try to determine the number of metal-metal bonds in a compound. So let's take example. We'll start from a basic example. Example number 1. We have a compound Mn2CO10. This is a compound. In this compound, we have to determine metal-metal bonds. So basically what we'll do, we'll determine TVE. TVE is total valence electron count. What are the valence electrons of manganese? They are 7. But there are 2 manganese atoms, so it is 2 into 7. Plus, carbonyl is a bidentate ligand. It donates 2 electrons. So basically, we have 10 carbonyls. So 10 into 2. So this comes out to be 2 7s are 14, 10 into 20, that's 34. So your TV comes out to be 34. In the second step, metal-metal bond will be equal to, metal-metal bond will be equal to TV 18 into N, 18 into N minus TVE divided by 2, isn't it? So what is N over here? N is the number of metal atoms, so N is 2. So we'll apply over here 18 into 2 minus 34 divided by 2. So basically this will come out to be 36 minus 34 divided by 2. So basically this will be 2 by 2, that's 1. So in this complex given over here, we have one metal-metal bond. This possesses one metal-metal bond. Metal-metal bonds is equal to 1. In this complex, metal-metal, the number of metal-metal bonds is equal to 1, isn't it? So from this information, from the number of metal-metal bonds, we can determine its structure. So we have manganese over here and we have manganese over here. Basically, we have one metal-metal bond. So whenever we have a metal-metal bond, basically it contains 2 electrons, one from this, one from this. This information will be important for the coming lectures. So we have 10 carbonyls, means 5 carbonyls belong to this manganese and 5 carbonyls belong to this manganese. So we have carbonyl CO, we have carbonyl CO, we have 3 more carbonyls, CO, CO, and CO. We have one more carbonyl over here. This is CO, this is CO, and these are carbonyls. So this will be the structure of this Mn2CO10. These carbonyls are known as terminal carbonyls. These all COs, they are known as terminal COs. There is one more category of carbonyls that is known as bridging carbonyl. We'll come to know about that. What is bridging carbonyl? Let's take example number 7. This is a very important example. I am going to discuss example of cobalt CO2 CO8. This is also a very good example. So in this case, first we'll determine TV. So TV will be equal to cobalt contains 9 valence electrons, 2 into 9, plus there are 8 ligands of CO. So 8 into 2, because basically this CO is a 2 electron donor. So this will be equal to 2 9s are 18 plus 8 2s are 16. This will be equal to 34. So now we have to determine metal-metal bonds. So how many metal-metal bonds will be there? There will be 18 into N minus 34, that is TV, divided by 2. So 18 into N basically is 2 over here. 18 into 2 is equal to 36. 36 minus 34 divided by 2. This will come out to be 2 by 2 and 1. Means this compound also contains one metal-metal bond. Over here, the compound given contains one metal-metal bond. Metal-metal bonds in this compound is equal to 1. But this compound has 2 different structures. Basically, this is important. This thing is very important. Cobalt carbonyl, it contains 2 different structures. It contains 2 different structures. In solution phase, the structures are in solution phase. In solution phase, the carbonyls are, the COs are only bridging. The carbonyls are only terminal. These are only terminal. So what do we mean by this? These are only terminal, means in solution phase, the structure will be this. This is one cobalt, this is other cobalt, there is one metal-metal bond, and there are 4 carbonyls attached. These are the 4 carbonyls attached. Again, there are 4 carbonyls attached. These are called terminal COs. So basically, these will be your terminal COs present in this compound. These are terminal COs. But in the solid state, the structure has been found to be different. We talk about in solid state, this is in solution phase. This structure is in solution phase. But in case of solid phase, what has been observed? It has been observed that 2 of these COs, they are not terminal, they are bridging. Means the structure will be like this. This is cobalt, this is cobalt. So over here the CO is a bridging ligand, and over here the CO is a bridging ligand. This ligand is known as bridging, which binds 2 metal atoms, that's known as bridging ligand. Over here 2 COs are bridging, and remaining 4 remaining how many? 2, 1, 2, remaining 6 COs, that is CO, 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 we have one more CO, we have one more CO, they are terminal. So this compound, the information which is over here, this compound in solid state contains 2 bridging COs. How do we know that it contains 2 bridging COs? What is the reason? The reason comes from IR spectroscopy. Once we finish 2 or 3 lectures, then we'll discuss stretching frequency of these carbonyl ligands. The stretching frequency of terminal carbonyls is different from that of the stretching frequency of bridging carbonyls. So over here, all the carbonyls are, you can see over here. Now let me take a different ink. Over here, all the carbonyls, they are terminal. This one is terminal. These all are terminal. So terminal carbonyls show only one stretching frequency. Therefore, in this compound, when in the solution phase, only one IR stretching frequency per carbonyl is observed. But when the structure was elucidated in solid state, 2 different types of stretching frequencies have been observed. One for these terminal carbonyls and the other for these bridging carbonyls. They show different terminal frequency. Different IR stretching frequencies. That's why this structure has been observed. Now let us take other examples. Let us take example number 3. Let us take example number 3. So we have example number 3, Fe2CO9. Let me take this Fe2CO9. Yes, Fe2CO9. So first we will determine TVE. So basically Fe contains 8 valence electrons, 2 into 8 plus 9 into 2. Isn't it? So this comes out to be 16 plus 18. 18 plus 16 is again 34. Isn't it? 18 plus 16 is again 34. So TVE comes out to be 34. So now we have to determine metal-metal bonds. So metal-metal bonds will be equal to N into 18 into N minus TVE, that is 34 divided by 2. So N over here is 2, 18 into 2 is 36. This comes out to be 2 by 2, that's 1. So this compound also contains one metal-metal bond. So now let us draw the structure of this compound. So structure is determined with respect to metal-metal bonds and with respect to IR stretching frequencies of carbonyl ligands. If only one stretching frequency is observed, then there are only one type of carbonyl ligands. If 2 different stretching frequencies are observed, then we have 2 different types. Then there is also bridging carbonyl ligand. So we have Fe over here and we have Fe over here. There is one metal-metal bond. Isn't it? There is one metal-metal bond. So in this case, the bridging carbonyls are 3. It has been observed that in this compound contains 3 bridging carbonyls. So this is one bridging carbonyl. There should be one more bridging carbonyl, that is this. In the coming lectures, we will discuss the stretching frequencies of these carbonyls. There is one more bridging carbonyl, that is this. So these 3 carbonyls, they are bridging, and the remaining 6 carbonyls, they are terminal. So one carbonyl over here, one carbonyl over here, one carbonyl over here. So we can have 3 more carbonyls over here. They are terminal. So this will be the structure of this compound. The structure of this compound will be this. So now let us take other series of these questions as examples. That's example number 4. In case of example number 4, let us take these type of complexes. M3 clusters, M3CO12. So where M over here is, in this case, M is a metal, and this metal may be your iron. It may be iron, it may be ruthenium, or it may be osmium. These 3 belong to the same group, all have 8 valence electrons. So if I take one of the example among these, rest will be same for all the cases, isn't it? So in this case, this M is iron, either iron or ruthenium or osmium. They all have 8 valence electrons. So I'll determine TVE for this. TVE will be equal to basically 3 total valence electrons of metal into metal contains how many valence electrons? This group contains 8 valence electrons plus 12 into 2, because we have 12 ligands and each carbonyl denotes a pair of electrons. So 3 8s are 24. So this will come out to be 24 plus 24. 24 plus 24 is equal to 48. Now we have to determine metal-metal bonds. To determine metal-metal bonds, we use the formula 18 into N minus TVE divided by 2, isn't it? So we have 18 into N. This is 18. N over here is number of metal atoms, that is 3. That means 18 into 3 minus TVE, that's 48 divided by 2. So this will come out to be 54 minus 48 divided by 2. So this will come out to be 6 divided by 2. 6 divided by 2 is 3. So this complex contains these type of complexes. They contain 3 metal-metal bonds. Or here you can have 3 metal-metal bonds. Clear? So if we have 3 metal-metal bonds, we can arrive at the structure of this compound. So we can have metal atom over. Let us take iron, ruthenium, or oxygen, anyone. Let us take iron. Iron over here, iron over here, iron over here. These are 3 metal atoms. There are 3 metal-metal bonds. This is one metal-metal bond. This is second metal-metal bond. This is third metal-metal bond. Isn't it? So in this case, what has been found? 2 carbonyls have been found to be bridging carbonyls. So we can have bridging carbonyl over here. And we can have one more bridging carbonyl, that's this bridging carbonyl. 2 of the carbonyls have been found to be bridging carbonyls. And the rest 10 have been found to be terminal carbonyls. So over here we can have terminal carbonyl 1, 2, 3. Over here we can have terminal carbonyl 1, 2, 3. Since they contain also bridging, over here we can have 4 terminal carbonyls because there is no bridging carbonyl present. Over here you can have one more carbonyl. So this will be clearly be the structure of this type of compound. Like that you can have compound like Ru3 CO12, the structure will be same. OS3 CO12, structure will be same. So in all these complexes you can have 2 bridging carbonyls. This question has been asked in NET exam. So question was like this: you are given a compound Ru3 CO12 and you are asked to know about how many bridging and terminal carbonyls are present in this compound. So if you remember this type of example, you can clearly understand this thing. But what is the reason? The reason again lies on the stretching frequencies. The stretching frequencies, that's IR spectra data, determines the structure. So for that IR spectra data, we have to wait for 2 or 3 lectures, and then we will understand how we can have 2 different types of stretching frequencies and the bridging and terminal ligands in a particular compound. Clear? Over here, one thing is important. What's important? Out of these 3, only this iron, I mistakenly I have said a wrong word. Over here, only in this case, if we have iron carbonyl, there are 2 bridging carbonyls. But in case of ruthenium and osmium, like I have OS3, CO12, in these 2 cases, there is no bridging carbonyl. In these cases, there is 0 bridging carbonyl. There's one more reason that explains this: 0 bridging carbonyl. Now, what is that reason? The reason is because on moving down the group, we have iron, we have ruthenium, we have osmium. Size increases. Since the size of these 2, which is larger compared to that of iron, so they can easily accommodate terminal carbonyls rather than undergoing bridging carbonyls. Isn't it? So size is the reason. What is the reason? Size is the reason. So out of these 3, only iron contains 2 bridging carbonyls. So now let us move to the next type of the problem. So if I have example number 5, the example number 5 will be like this. I have a cobalt 4 CO12. So I have to determine number of metal-metal bonds. What I am going to do, I will determine TV. TV will be equal to 4 into valence electrons of cobalt. That's 4 into 9 plus 12 into electrons donated by this ligand, carbonyl ligand. That is 2 into 12 into 2. So this will come out to be 4 times are 36 plus 24. That will come out to be 60. So here we have to determine metal-metal bonds. So how you are going to determine metal-metal bonds? Metal-metal bonds will be equal to 18 into N minus TVE. Isn't it? Divided by 2. So N over here is 4. 18 into 4. 18 into 4 is equal to 72 minus 60 divided by 2. So this will come out to be 12 by 2. 12 by 2 minus 6. So in this compound, there are 6 metal-metal bonds. There are 6 metal-metal bonds present in this compound. I hope this thing is clear to you people. In this compound, there are 6 metal-metal bonds. Isn't it? So now you can draw the structure. I will write over here. It is structure. In its structure, there are bridged carbonyls. 3 carbonyls, 3 COs, they are bridging. They are bridging between 2 metal atoms. And the rest are terminal. 3 COs are bridging and the rest are terminal. I hope this thing is clear to you. Now let me take one more example, example number 6. We can now draw its structure. We can have 4 different carbonyls. This is one carbonyl. This is second carbonyl. This is third carbonyl. This is fourth carbonyl. This is one metal bond, second metal bond, third metal bond, fourth, fifth, and sixth. These are 6 metal bonds. And there are only 3 bridging carbonyl ligands. Let us say there is one bridging carbonyl ligand that's over here. Between this is carbonyl. Between this cobalt and this cobalt. This is a bridging carbonyl. There is one more bridging carbonyl over here between this cobalt and this cobalt. Isn't it? So let us say there is one more bridging ligand over here between this cobalt and this cobalt. Then the rest will be terminal carbonyls, isn't it? So we have put over here 3 bridging carbonyls, then the rest will be terminal carbonyls, isn't it? So let us take one more example. Let us take example of this type. IR4 CO12. Or let me take one more different example. Let me take this type of example, OS4 CO14. OS4 CO14. This is an example. So osmium is also a member of iron group, or here the valence electrons of osmium will be 8. So we'll determine TV. TV will be equal to 4 into 8. Plus this is 14 into 2. Because carbonyl denotes 2 electrons, we have 14 such carbonyl ligands. And this will be equal to 32 plus 28, that is 60. And then we have to determine metal bonds. So how you can determine metal bonds? 18 into N minus TVE divided by 2. So N over here is 4 number of metal atoms, means 18 into 4 minus 60 divided by 2. 18 into 4 is 72. 72 minus 60 divided by 2. So this will again come out to be 12 by 2. So this comes out to be 6, means this cluster also contains 6 metal bonds, isn't it? This cluster also contains 6 metal bonds. Clear? I hope this thing is clear. This cluster also contains 6 metal bonds. Isn't it? This cluster also contains 6 metal bonds. Now let us take other examples. So let me take one more example. OS4 CO15. Let me take one more example. OS4 osmium 4 times CO15. So over here you have to determine TV. Osmium contains 8 valence electrons, so 4 into 8 plus 15 into 2. So this will come out to be 32 plus 30, that is 62. So over here we have to determine metal bonds. Metal bonds will be equal to 18 into N. 18 into 4, that is 72, minus TV, that is 62 divided by 2. So this is 10 by 2. 10 by 2 is 5. So this compound contains 5 metal bonds. It contains 5 metal bonds. So now it is easy. So again, if we have again this type of compound OS4 CO60. So how many metal bonds? That is TVE will be equal to 4 into 8 plus 16 into 2. 4 into 8, 32 plus 32, that is 64. So again, metal bonds, what will be the metal bonds? So metal bonds will be equal to 18 into N, that's 18 into 4, that is 72, minus 64 divided by 2, that's 8 by 2, that is 4. So this compound contains 4 metal bonds. I hope this thing is clear to every person now, how to determine metal bonds, isn't it? So lot number of questions, basically 2 or 3 questions have been asked this year, that is in January 2022. That is June 2021 exam. Lot number of questions have been used. In the next lecture, what we will do, we will determine unknown quantity. Unknown quantity means we will determine number of COs. In the next lecture, we will determine number of COs. If we do not know the number of COs over here, we can determine it. Number of carbonyls, that's unknown quantity. And we will determine charge on the ion, charge on the cluster. We will determine charge on the cluster. Charge on cluster. So for example, I will take 2 types of examples and we will solve these examples in the next lecture. I have this type of example, neta 5 C5H5 Mn. This is a complex of manganese. Over here it is bonded to neta 5. Neta 5, it has hapticity 5, means it's a 5 electron donor. CO whole X whole twice. So over here you have to determine unknown quantity, that is this X. In the next lecture, I'll show you how to determine this unknown quantity. A question has been asked on this also in net and gate exam. Question have been asked. And one more thing we'll determine in the next lecture, that is charge on the cluster. For example, this type of compound over here, CO3. Over here I have a charge X. This is the unknown quantity. We'll know how to determine this unknown quantity. And then we'll discuss other type of clusters, that's high nuclearity clusters. Isn't it? There is a different approach we have to apply for high nuclear clusters. So I hope this thing is clear to you. Please share, like, and subscribe this channel. Share with your friends. Thank you. Thank you for being with me, and thanks for watching this lecture.